Thank you, Guido, for the presentation, and thank you for inviting me to present at this session here. It's really a great pleasure to be back. It was so lovely to see everybody again yesterday. It's now approximately 20 years that we are around, and as we discussed yesterday, we haven't really changed. So thanks so much, for everybody who makes this place always like coming home for me, and I really appreciate it so much. So the title of my presentation today is Seismic Assessment of Historical Stonemasonry Structures, Modeling Sensitivities and Opportunities Through Digitalization. Apologies for the very long title. Actually, on a much more personal note, it's actually not that long ago that I started looking into historical structures, and the reason is really the Basel project that we had the pleasure to conduct with the masonry group here in Pavia, and that really hooked me completely, and then since then I have been dedicating a lot of my research time really to historical stonemasonry structures. And today I'm going to talk about 3 small topics. All are related to equivalent frame modeling. In the first one, I will show you where we do a post-diction of a test. In the second one, I will show you some prediction of a test and us waking up to the fact that this is magnitude more difficult. And in the last one, I will just try to quickly give you a glimpse on what we are trying to do in order to automate basically the model generation for equivalent frame models. So let's start with the post-diction test. So as you know, in stonemasonry buildings we have of course in-plane failure modes, but because often we have also these timber slabs that are very poorly connected to the walls, we also have a lot of out-of-plane failure modes. So often for the analysis of these buildings, of course we use equivalent frame models, as many, they were really very much developed here, and of course in particular also by Andrea Penna during his PhD thesis. So you know that they're really modeled with, where the piers are modeled with vertical elements, the span bones with horizontal elements, and then the rigid nodes, and then we end up with that frame. So a lot of work, as I said, has been done on that, and many macro elements have been developed, and as I said before, the one by Andrea Penna is probably the one most widely used nowadays in research and then also in engineering practice. So there's a lot of choice available, but what they all have in common is that they really focus on the in-plane response. So what we wanted to do then together, also with Andrea, is to augment basically the macro element to also capture the out-of-plane response, because we felt that would really give us quite a few new basically analysis possibilities. So we did that by basically including some additional degrees of freedom, turning it into a 3D element, and then adding also some flexural degrees of freedom for the out-of-plane response, so that at least we can capture the simple sort of out-of-plane bending moment where we have a hinge at the mid-height, or of course then really so whole over turning of the walls. And that is really the work by Francesco Banin in his PhD thesis. So here you just see a little bit on what that element, or how that element behaves. So for example, if you have a U-shaped wall and you do sort of a push over here, then you can really see so that you get here sort of the out-of-plane behavior. Here you see the force displacement response on the right-hand side, and you can also model that the beams sort of slip off. This is of course rather important, because the connections, as you will see in a moment, is really a very important modeling detail when we model the out-of-plane behavior. But if we include the out-of-plane behavior, then we can really sort of model the incremental, for example, do incremental dynamic analysis, and in some analysis for some ground motions it will fail in plane, and some others it will fail out of plane, and we really can bring the two analysis streams together. As I just said, so if you want to capture out-of-plane behavior, we really need to model also the nonlinearity of the connection. So in particular of the wall diaphragm connection, but also of the wall connection. So in this we do with nonlinear springs. And all these models have been implemented in OpenSeas, which we basically use as our basis. So now we went back to some tests, the very famous sort of shake tape tests on 3 stonemason buildings that were conducted here in Pavia in 2014. And so 3 buildings were tested, of which the first one was an unretrofitted configuration and the other 2 were retrofitted configurations. And these other 2 buildings, they had already been modeled very successfully by Andrea Penna and Ilaria Zenaidi. So there's really nothing to add. You see here the comparison between experimental results and numerical results. The experimental results in black and the numerical results in red and blue, respectively, for the 2 buildings. There's nothing to augment here. So the one that hasn't been modeled yet with equivalent frame models is really the building number 1. And so this is the unretrofitted configuration, and this wasn't the one that we tried to model here. So this configuration has flexible timber diaphragms and a flexible roof, and also the timber beams are just sitting on the walls. We didn't try to reinvent the modeling. We really just used exactly the model that was developed by Ilaria and Andrea. So with the same parameters, all the same, with the same discretization, of course now with a new macro element. Also the diaphragm parameters and the friction coefficient, we used new parameters because in the previous models, of course, the diaphragms were retrofitted, so we had to recalculate the diaphragm stiffness, but we did that really on first principles based on the model by Brignola, and the friction coefficient we had derived from direct shear test between timber and mortar. So there was really no calibration in it. For the damping model, Andrea Penna, in his nonlinear analysis, he had recommended 2% damping for near collapse, so we used in the end 2.5% damping, but we used second stiffness and mass proportion damping at the first and sixth mode. And if we do that, then we get actually quite a good correspondence between numerical and experimental results. Here in blue you see the numerical results, so that's for the 5 runs that were done on this building with increasing PGA. In green you see the experimental results, so that's for the top displacement. You see here a certain range of experimental results. This is just because we derived these top displacements from accelerations that were measured, so we had to integrate twice and then we had to apply a filter, and the results depended a little bit on the filter parameters that we used. So this is why we're plotting here the experimental results as a range rather than as a one value. But you can really see that overall our prediction really corresponds quite well with experimental results. Also in terms of failure mode, we are not too far away. I would say our failure mode is a little bit more gable out of plane failure than also the first story, but even the first story is activated a little bit. You clearly see that the spandrel here opened up the top spandrel, so we see that also the in-plane walls are activated a little bit. So with that we can really say, well, now we have an equivalent frame model that at least can capture some of the out-of-plane failure modes. So the basic out-of-plane failure modes we can reproduce. And then of course we can also use it to investigate some retrofitting interventions. And here we focus, for example, on the retrofit interventions on the connections, which was also not so easy to do earlier. So in the black you see here the original configuration, so where the diaphragms were flexible and then the connections were just a friction connection. In blue you see the result if we just retrofit the diaphragm connection. And so if we just retrofit the diaphragm, so we make the diaphragm stiffer with an additional layer of planks. And what you can see is that this increase in diaphragm stiffness has really an effect, but only up to a certain limit PGA. And beyond that, there's basically no effect of increasing of stiffening the diaphragm only. Why? Because at a certain PGA level, then you really get sliding in all the joints between the diaphragm and the wall, and then the effect of stiffening the diaphragm is basically for nothing. Of course, the best result we really get if we improve the connections and the diaphragm, which is here represented in the red line. Also the effect of the connections we can see here when we look at the relative displacements between diaphragm nodes and macro element nodes. If the diaphragm is unretrofitted and if it's very flexible, actually the relative displacements are not so large because there's not that much sliding, but they are not zero. If we have the diaphragms retrofitted, but the connections is not retrofitted, then of course we get really that relative displacement between the macro element nodes and the diaphragm nodes. Of course, if we also then retrofit the connections that we model just as equal degree of freedom constraints, then the nodes are always in the same place as the diaphragm. Okay, so this is really the first part of the post-diction. So basically showing that with that augmented macro element model, we can really capture also the out-of-plane response. It's important to also include the nonlinear connections in order to activate these out-of-plane mechanisms, and it really allows us to study a wider range of failure modes through equivalent frame models, which are really so widely used in engineering practice. As I said, the nonlinear connections play a key role for the out-of-plane response, in fact also a bit for the in-plane response, in particular for the in-plane response of spandrels, because with the nonlinear connections we can now really allow the elongation of the spandrels depending on the diaphragm stiffness and the effective connection. So in the future we really want to invest more in the spandrel element modeling and also exploit some of the modeling capabilities that we haven't really used yet, that Francesco has coded into that macro element, and this is in particular with regard to the drift capacities, making the drift capacities a function of the axial load ratio as of the shear span ratio and so on. So this is for the future to come. In case you're interested in these models, they're all publicly available. The links are in the papers or in, you can just write me an email. So now let me go to the second part, which is a prediction of a shake table test that we had the pleasure to conduct at ALNEC a short while ago. So actually when we looked at the literature, we didn't find so many blind prediction studies on masonry structures. So we found the one, of course, from the University of Minho, where it was really the focus on the out-of-plane loading, then the one focusing on the Dutch building systems, but this was a quasi-static cyclic test, so not exactly representing full seismic loading. And then, so this was really one of the key motivations for conducting a new blind prediction test, on this time on a masonry aggregate, so something that was considerably more complex than what has been analyzed before. And if I have missed here any blind prediction competition on masonry structures, I would love to hear about those. So if we compare a little bit the failure modes that were behind it, as I said, the first blind prediction competition was really focused on out of plane, the second one on in plane, and we had really now the mix. Also in terms of diaphragms, it will become a lot more complex. So the first one had no diaphragm, the second one basically rigid diaphragms, and we had flexible diaphragms. And as I said, we also have an aggregate, so that means here the smallest aggregate possible is 2 buildings. So here's just some more information on the shake table test that was financed through the SARA program, so it was a SARA AIMS test. As I said, it was done at ALNEC with Antonio Correa. So here the geometry of the test unit. So we have the 2-story test unit, which would basically be the test unit that was constructed first. And then the 1-story test unit was constructed second. And here, really, the unit was sort of just constructed against the unit 2, so it's like a C-shaped unit. It's basically missing one wall. It's using the wall of the unit 2. It's a stone masonry structure, so this is how it looked like before the plaster was applied. And here you see the building with the plaster, and I'm just running to give you an idea the video of the last test. And you see here we get a lot. This is a longitudinal test. That we also applied excitation in a transversal direction and also bidirectional excitation. You see we get here quite a lot of rocking on the top floor. So when we modeled that building, we used the same modeling approach as before. The only thing that we developed really specifically for this aggregate was really a nonlinear connection, an element for the nonlinear connection between the units. So this is now basically a spring for modeling the bidirectional friction between the 2 units that we used really to connect the lower unit to the higher unit. And as I said, we organized that was our EPFL model, but as I said, we organized the blind prediction competition, and here we had really 12 participants with, I think, total 13 models, mainly from academia, but also 2 contributions from industry. And when the blind prediction submissions came in, and we then plotted the EPFL model against the distribution of the prediction by the participant, we thought, not too bad, we are around the median value here. But of course, one thing that struck us immensely was really the large scatter in predicted results. So basically, some people predicted close to 0 displacement demand for 75% input. We had, and some close to 140 millimeter roof displacement demand for the higher unit. The scatter was even larger when we looked at the interface opening, so the opening between Unit 1 and Unit 2. But for all the values that we requested, we lay approximately in the middle, and we came a little bit to the world when we really then saw the experimental results, which were completely not where the median prediction was. So here the experimental results in green. Of course, the experiment is never exactly what we had as input, but we made a comparison. I think that there's a reasonable comparison to be made, and the discrepancy doesn't come from the discrepancy between input and output, I would say, or not the largest part of it. So what you can clearly see is that the majority of participants, including us, really underestimated the displacement demands considerably. So these are really still ongoing investigations, so not everything is settled yet, but here just some first results. One thing that was really striking is that the displacement demand estimates that came from discrete element models, so here abbreviated as DEM, were much better than from finite element models, so equivalent frame models, shell models, or solid finite element models. Those models, as I said, including ours, we underestimated the displacement demand considerably. That applied to the roof displacement, as I said, and also in particular also to the interface displacement. On the base here, the picture is a little bit different. There, the finite element models perform better than the discrete element models. If we go back to our own model, actually the failure mode we didn't predict so badly. We had really that rocking of the second story, and also the sort of the out of plane flapping of the freestanding walls of the lower unit. So I think in terms of failure modes it was really quite well. But as I said, the displacement demands we really underestimated, and we're still investigating why our finite elements analysis were basically so wrong, so much off. One thing is really clear: we were too stiff, and that's, I think, applied really to most of the finite element models. We had used the E-modulus that was obtained for vertical loading instead of the E-modulus that was derived from the quasi-static cyclic test. This is really an oversight, and we should have known that. Another thing which was important was that we had still used our old damping model then, because in fact these analyses had been done before the previous one. And this was an initial stiffness proportional model and mass proportional model instead of a second stiffness proportional model. And with that, we just don't capture the out-of-plane response very well. We can capture sort of the onset of the rocking, but not really the rocking very well itself. So you see here in the bottom just a comparison of the two damping models for the macro element if we use, if you have a freestanding body. So what Francesco also did, he developed basically a second stiffness proportional damping model, where the second stiffness is basically this initial stiffness reduced by a factor, B second, and that B second is basically calculated as the ratio of the second stiffness to the initial stiffness for 6 degrees of freedom in our macro element. So for the for the 6 bending degrees of freedom in the two end sections and in the middle section. And then he also does some clever things so that we don't get too low or too high values here. So this is clearly something that we need to update in our model. And then but I don't think this will fix entirely the problem, so we still have to look into what other problems there were. So just to summarize quickly the findings from the blind prediction competition, if we compare very broadly, then we can really say the discrete element models have really performed well in terms of failure mode and displacement demands. They have underestimated the base shear forces. On the finite element model side, it's really basically sort of the opposite. They estimated well the base shear forces, but completely underestimated the displacement demands. The displacement demands, as I said, mostly because they're too stiff. For us, wrong damping models, I think some other used wrong damping ratios or not very good estimates of the damping ratios. And then another problem in other finite element models was also that the nonlinear connections were not modeled between diaphragms and walls. And if they were not modeled properly, we also saw that the failure modes were not captured very well. One other thing that is, of course, striking is the significant coefficient of variations between the blind predictions that came in at the significant damage level. So for the global displacements, we had coefficient of variation of 160 to 180%, local displacements even higher, base shear a bit lower. And this is considerably higher than what was seen in the previous 2 blind prediction studies. And the reason could, of course, be that we have a larger variability of modeling approaches that was used in this blind prediction study here. In the others, it was more focused on equivalent frame models, for example, for the second one. We have also a structure which is considerably more complex, and we have the fact that the nonlinear connections play here an important role. Nonlinear connections between the wall to diaphragm, but also between the units, the 2 buildings. And I think altogether that really led to these very high coefficients of variations. I think it would be very interesting now so we're just working on a special issue on these on the tests, and then also on the entries basically made by the various people. So all the teams, they write one article on their model, and I think it will be very interesting to see the analysis of the participating teams to what were the factors that made that created sort of this offset in prediction to the observed values. I think that there's really a strong need for further blind prediction competitions on the seismic response of unreinforced masonry buildings. It's really something much more awakening than doing post-diction results, where you in the end always have, or very often you get very good matches. So also here, of course, all the data is publicly available. In fact, we've already put it on the DesignSafe platform for testing it a little bit, and also for sharing it early on with the participants in the blind prediction competition. So now I just want to come to my very last part. That's really just sort of a snapshot of what we are also doing. So with regard to equivalent frame model spaces, so the whole pre-part to how to arrive at an equivalent frame model. And there in particular how to arrive as much as possible in an automatic way at an equivalent frame model. So here the idea is really to build up an image-based post-earthquake assessment pipeline where we can take images with drones or handheld cameras from the building. We can detect then the damage on these structures. We can also build a 3D model from it. We can merge the 2 and also build then in the end a finite element model for it, an equivalent frame model for it. So we're still working on that, of course, a lot. So not everything is completed here, so just some preliminary parts of it. So for the damage detection, we have done some work using machine learning techniques, so convolution neural networks, and have also benchmarked in particular with regard to digital image correlation results that we obtained in the lab. And that allows us now really to identify the cracks rather well in the building, and then to project them then later also on the 3D model. We have also worked a little bit on identifying just from images the crack kinematics of the cracks, so that we can differentiate easily between shear cracks, flexural cracks, and mixed mode cracks. On the 3D model side, we have developed a pipeline that sort of basically uses many images and uses structure from motion techniques in order to generate basically a 3D point cloud, and then really approximates using polyfit functions and then a polygonal surface generation, and using again machine learning techniques that defines the openings, the corners of the openings. Basically, this is segmentation of the facade into facade openings and corners of the openings, and then using some algorithms to come up with window layouts that are reasonable. We then obtain an LOD3 model, so a model where we have the shape of the building and the openings. And this model can really serve as input for an equivalent frame model. We have tested it now on quite a few different structures. So the last step that we are really working on is now really also the damage triangulation basically on the digital twin, so that in the end we have sort of an augmented digital twin where we have the damage and the geometry on that. And here just some also an application from Croatia. Future developments, we still have to include basically information from the interior. For the moment we have just done it from the exterior. The segmentation to macro elements, I know there's also some work done here. And then of course the effect of the damage on the macro element properties, so that we can analyze really also the damage structure and not just the working structure. With that, I'm at the end of my talk, and I thank you very much for your attention. I'm open for questions.
Thank you, Katrin, for a very interesting presentation. Are there any questions from the floor? Michele.
Thanks, Katrin. Great to listen to you. In the first part of your presentation, there was a slide where you were comparing three curves, a gray one, a blue one, and the red one. And I think you stated that the red one, which was the one where you were been strengthening both the floor frames and the connection, was showing a significant improvement in the response. I have difficulties in seeing any significant improvement, because I think that in terms of probability of collapse, these curves are really more or less the same. You know, if the last point is the collapse point. I mean, the red one even seems to have a lower displacement capacity without changing significantly the strength. So I expect that in terms of probability of collapse should be the same. Maybe I'm wrong.
Yes, so I haven't looked at the probability of collapse. These are really just either curves for one record. So it's not yeah. I think one thing that changes, of course, is really sort of the flexibility of the roof diaphragm, and that changes then also the second story displacement. We get some amplifications there. But I would still vouch for retrofitting connections.
If I may comment on this, it is a comment, and I'm not giving any solution to the problem. This is something that we noticed also by looking at the experimental results when we tried to plot the results in terms of base shear versus, let's say, top displacements of the three different models that we tested on the shake table. So by simply looking at the, let's say, this sort of force displacement envelope that recalls a pushover analysis, whereas in reality it is coming from shaking table test, you don't really see the improvement in terms of shaking intensity that the three different models could resist. So as a matter of fact, when we compared the performance of the three different models, from the unstrengthened to the fully strengthened model, by looking at other parameters, other, let's say, seismological parameters describing the table motion, then the improvement was much more dramatic. Okay, so there must be clearly something related to also, let's say, energy dissipation mechanisms that are activated in some cases and are not activated in other cases that you cannot see on this type of plot, but they, you can then detect them when looking at the dynamic response.
I mean, here it's really that with the retrofitting, then we remove basically the out-of-plane rocking of the thing. So we reduce basically that displacement capacity that we have there, but it's not really that this makes it worse, on the contrary. Yes, but we could think of how we could plot it better to make that clear. That's true. Point taken.
Simone.
Thank you, Katrin. I was just curious about the prediction exercise that you perform. If you also perform dynamic analysis and dynamic identification, of your specimen and how the results are in comparison with those of the model, because you said that there was a big difference in stiffness, and from there it should be something that rise up.
Yes, I don't have now the exact. That was done. We have also compared the predictions with that. I don't have the exact numbers now in my head, but I think that the difference in stiffness is around 30 to 40%.
Are there any other questions from the floor? Okay, if not,